If you guys have ever watched my L-Systems course, then you'll know a little bit about packed geometry and what that is. But for those of you who haven't had this conversation before, let me explain what packed geometry is. And we're going to use this diagram to try to understand what's happening and why you might want to use this. So imagine that we have a tree, and this tree is represented in the computer as a bunch of different things written down on a scroll. Just imagine that you had a piece of paper and you wrote down everything about this tree. This tree might contain points, so the points might have locations, and the entries might look something like this. If we have, let's say, point number 1, there's the location. Point number 2, here's another location. And so on for, let's say, 1,000,000 points that exist on this tree. We have all that information. That's our P attribute, right? And we also have any additional attributes that get stored with the points or with the mesh. And so as a result of all this information, which describes the tree, we're left with 1 megabyte worth of data being stored on this scroll. Now, if we copy this a bunch of times, we have a bunch of scrolls. As you can imagine, we would have 4 megabytes in size. So somebody at one point or another came up with a really cool idea. They said, hey, why don't we just point towards this scroll right here instead of writing out the same things every single time? If this is the same tree, there's no need to write this out 4 times and take up 4 megabytes in space. So instead, we just say, hey, look over there, dude. This is 400 megabytes in size. That's 0.0004 megabytes. And just by saying that, we've created an instance, well, essentially an instance, of what that tree is. So this gets stored to RAM. That is the original tree gets stored to RAM. And the scroll just says, hey, look at this tree. You'll find it in memory, or you'll find it in RAM, which is like, you know, this stuff right here. So that's basically what happens. As I mentioned before, 4 megabytes in size versus 1.0012 megabytes in size, and we're representing the same exact thing. Now, one thing to know here is that, as I mentioned before, these packed primitives, right, this little scroll that just has this look over here written down on it, this is represented in Houdini with a singular point. So one thing to add to this is, let's say that we're in Houdini, right? These trees might have 1 point near the center, like this, and that represents this scroll right here. So here's the classic example of what this does for you. We have all of these Eugenes copied, and I have lots of different Eugenes going on, right? I'm at 66% of memory, which on my PC is 42 gigs of RAM being used. Now watch what happens when I change a regular Eugene into a packed primitive. I go to pack like this, and now I copy the points. Watch what happens. Look at that. Smooth. I can actually just, you know, navigate around like this. If I go back to my memory, look at that. Memory went way down. I'm at 26 gigs. And honestly, most of that has to do with the Premiere session that I have open on the side that you can't see. So that gives you an idea of what you can do. Also, there's these boxes here, and that's just a viewport optimization that Houdini automatically does so that you can tumble around really quickly. So anyway, again, that compared to, let's say, not using this pack. Yeah, there we go. So now you can really see that we're just chugging along. And that is why you should pack stuff. Now, again, this only works if you have the same exact object for each one of these instances. You can't have a different version of Eugene on these different objects, okay? It needs to, again, refer to the original mesh, which lives in your memory. But anyway, that's what packed geometry is all about. So now that we know what a packed object is, we can figure out what this RBD packed object is all about. The RBD packed object assumes that you are using packed geometry, and the RBD packed object will simply change the transformation of that point, which represents each piece of packed geometry. Particle operations, or POPs, will apply to RBD packed objects because each piece is represented by that singular point. The most common way of creating collision geometry is for the solver to use this convex hole option. This will simplify the geo of each piece as it goes to simulate, and simplifying the shape of each piece helps the solver because there aren't as many points for it to think about on each substep of the simulation. The RBD packed object may not be compatible with some other solvers though, so this object is ideal for most situations and should be your go-to DOP unless you have a reason to do something else. So anyway, that's all kind of stuff that we've talked about here and there. Here is Eugene. This is those convex holes that we saw. And again, in the middle of each one of these holes is a packed piece, is the point, which uses POPs. So if we want wind, drag, pop fan force, the cool thing is we can use all this stuff. It'll affect the transforms on the points, and then eventually we'll just take those transforms and apply it to the high resolution geometry. In the next video, let's go ahead and move forward with this packed object idea, and we'll go from there.